Welcome to qnawire.
Here, we've defined both the tension and velocity for a seat on a swing ride. Now, we'll start like we do with most of our problems by drawing a free body diagram. If the red dot here is the seat, we know that there's a force of gravity pointing straight down, as well as a force of tension pointing in the direction of the swing ride. Now, the force of tension can be split into two components. The y component, right here, and the x component over here. Now, using this information, we can solve for our tension. So as we can see in the free body diagram, the vertical component of tension is what must balance out the force of gravity. So Ty equals mg. Now, when we look at our drawing, we can also see that our tension must be equal to the cosine of our angle theta between our seat and the vertical. So T cosine theta equals mg, and T is mg over cos theta. Now, we know m, we know g, and we're given our angle as well, so all that's left to do here is plug in, which we're going to do up here. And we find that our answer is equal to 179 kilograms times 9.8 meters per second squared. You write that a little bit neater. 179 kilograms times 9.8 meters per second squared, all over cosine of 60. When we plug that into our calculator, we get that the tension is equal to 3,508.4 newtons, and if you want to round to the next tenth, that would just be 3,510 newtons. If you want to double check, you can also look at your units. Our units when we solve the problem are kilograms meters per second squared, which is equal to newtons, so therefore our answer makes sense, and we are in fact working in units of force. And so 3,510 is our answer to part A. Now the problem asks us to find the velocity, that our chair is traveling in. So let's go back to our free body diagram. As we can see here on the left, the force that's pointing toward the center of our circular motion is the horizontal component of our tension. Therefore, that horizontal component must be responsible for the centripetal force. So Tx equals mv squared over r. Now, if the y component of tension is t sine theta, or t cos theta, then our horizontal component must be t sine of theta. And that is going to be equal to mv squared over r. Now, solving for v, we find that v is equal to t sine theta times r over m. And now we realize that r is not actually given in the problem, but we can determine it very easily using trigonometry. So r, right, is this section that I'm dotting red right now. But since we know our angle theta and we know that our hypotenuse is 15 meters, we can see very easily that r must be equal to 15 times the sine of theta, since the sine of theta is equal to r over 15 by trigonometry laws. So we'll rewrite our equation for v, which we now find is equal to t sine theta squared times L, the length of a rope. We're going to plug in 15 for that in a minute, divided by m. And now we're going to plug in our quantities. So all that's left to do is plug this into our calculator. 5,008.4 newtons, that's our tension, times 15, our length, times sine of 60 squared, all over 179 kilograms. And I'll extend the radical, just to make it clear that 179 is also under there. And when we solve, we get that this is equal to 14.848, and our units work out to be meters per second, which makes sense. And so this is our final answer for part B.